Welcome to Chem Time.
Hello friends, welcome to the presentation. In the previous presentation, we discussed that there are two methods for determination of surface tension that are being used widely. And we mentioned one method in detail about the determination of surface tension experimentally in my previous presentation. And that instrument is known as stalagmometer. And today's presentation covers the experimental determination of surface tension using tensiometer. This is devised by Junoi and it uses a platinum ring. That is why this particular method is also known as Junoi ring method. And this method can be used for measurement of surface tension as well as the interfacial tension. Surface tension exists between the surface of the liquid and air. Interfacial tension exists between two surfaces of two invisible liquids. And in both methods, a ring made of platinum is slowly lifted, and this force required to lift the ring can be measured either in terms of surface tension or in terms of interfacial tension. The mathematical equation that is going to be used is F is equal to W ring plus 2 pi Ri plus Ra into sigma, where F is the force required to raise the platinum ring. W ring is calculated as weight of the ring minus the buoyancy force that is due to the part of the liquid below the surface. R small r is radius of the inner ring of the liquid film. Ra is radius of the outer ring of the liquid film. We can take an average of these two radiuses and define a capital R as Ra plus Ra by 2. With this, the F becomes W ring plus 4 pi capital R into surface tension. Now, the force is determined using an electrode balance, and knowing the force and the dimensions of the ring, we can determine the surface tension. The surface tension of some liquids at 20 degrees centigrade are: for water, it is 0.072 newtons per meter. For ethanol, it is 22 newtons per meter. For sodium chloride, it is 114 newtons per meter. For sodium dodecyl sulfate surfactant, for which the surface tension is 0.038 newtons per meter. The advantage with the platinum ring method is it can be used for determination of surface tension even for viscous liquids. But the drawback for this particular method is it requires a pool of liquid for measurement of either surface tension or interfacial tension. Now, coming to one IIT problem that is related to determination of surface tension of an eye drop. The problem given as: when a liquid medicine of density rho is to be put in the eye, it is done with the help of a dropper. As the bulb on the top of the dropper is pressed, a drop forms at the opening of the dropper. And our interest is to determine the surface tension of this liquid medicine. And we know as the drop formed at the beginning becomes spherical because it requires a minimum increase in surface area. Now, we need to develop an expression of our surface tension in terms of the small r and capital R and the density of the liquid. Now, this is the dropper and this is the drop. The dropper will have a radius of R and the drop will have a radius of capital R, and this small r is much smaller than the capital R. Now, as the liquid falls from the dropper, it travels in the form of a straight line and then becomes spherical. And there are two forces that influences this particular drop, or one is the surface, the gravitational force pulls the liquid down and opposed by the surface tension force. And there are two components of surface tension force, and that is the horizontal component of the surface tension is 0, and the vertical component of the surface tension is given by 2 pi sigma r sine theta, where theta is the angle between the drop and the dropper. Now, the angle can be expressed, the sine theta can be expressed as small r by capital R. So, we can write the vertical force in terms of surface tension as 2 pi small r into small r by capital R. As a result, we'll end up getting the vertical component as 2 pi sigma r square, small r square by capital R square. And this force is balanced by the gravitational force that is given by mg. And m can be replaced as density into volume of the drop. And volume of the drop, for a spherical drop, it will be 4 by 3 pi r cube. So mg can be written as g rho into 4 by 3 pi r cube. So equating these two forces, 4 pi 3 pi r cube or rho g is equal to 2 pi sigma small r square by capital R. We can arrive at an expression for surface tension as 2 by 3 capital R to the power of 4 by small r square into rho by g, where g is acceleration due to gravity. With this, I conclude my presentation. Our next presentation will be on the pressure. Thank you.
Request you to like, share and subscribe my channel.